All right, this is the last video before exam 3, and it covers graphing rational functions. So we looked at solving these, rational being functions that are fractions, and now we're going to be looking at this graph and its attributes as well. So we have a list here. We're going to kind of take the first one to go through the list, where we need to look for, what these things are actually finding, and how we can create the visual picture of this function. So the first one we have is f of x equals 2 over x minus 3. 2 over x minus 3. So we first run into the domain. So when we talked about domain earlier in the start of this course, we said that if our function is a fraction, where do our eyes have to go? Our eyes have to go to the bottom, and we have to worry about the denominator not being 0. So the same thing's going to apply here. That denominator cannot equal 0. So if I look just at the bottom, x minus 3, what's my one number that I can put in there and make that denominator 0? The answer is 3. So I can put in any x in the whole wide world, positives, negatives, zeros, small numbers, big numbers, fractions, decimals. But if I put in the number 3, that denominator becomes 0, and I'm not going to get an output function for me to be able to plot a point on this graph. So my domain is any x as long as it's not equal to positive 3. So if we're looking for the domain, our eyes go to that denominator, to that bottom, and that denominator cannot be 0. With this gap in the domain, with this 1x being stuck there, it's either going to translate into a hole or a vertical asymptote. So the hole and the vertical asymptote are associated with that domain, and we got to find out what's happening at 3 since we don't have an output value there. Well, a hole would occur is if I had a factor, both top and bottom, that was the same, that divided out. So I don't have a duplicate x minus 3 on top that would divide out, so I know that it's not going to be a hole. And we'll see an example as we move on through these where a hole shows up and how we would handle that. So if there isn't a hole, then that gap in our domain, that value that would make the denominator 0, is going to cause a vertical asymptote on the graph. So because x can't equal 3, we're going to have a vertical asymptote at x equals 3. We're going to have some kind of boundary that's blocking, I'm going to focus here, that's blocking when it can't be a positive 3. So domain, the list of our domain is either going to create a hole or create a vertical asymptote. Next we have horizontal asymptotes. And horizontal asymptotes come with its own rules. So on the side over here, I'm going to kind of make a list of our horizontal asymptote rules. These are our horizontal asymptote rules. And so here are the 3 things that can happen. I could have a degree higher in the numerator than I do in the denominator. If my degree on top is greater than my degree on bottom, when I talk about degree, I'm talking about this exponent. So on the top here, I have an x squared compared to an x to the first on the bottom. If my degree on top is greater than the degree on bottom, then I have no horizontal asymptote. So I'm going to say if my degree on the top is bigger, then I have no horizontal asymptote. Just not going to happen. Actually creates a slant asymptote, but we won't get into that. That would be a different course. The next thing that can happen is my degree on top is the same as my degree on bottom. My highest degree on top is the same as my degree on bottom. If they happen to be the same, then we have a horizontal asymptote at what we say the ratio of the coefficients. So I'm going to kind of put the note same co. So I'm going to do an example here. What if I had a 3x squared over a 1x squared? My degree on top is the same as my degree on bottom. So if that's the case, I look at the ratio of my leading coefficients. And what I have here really is 3 over 1. So I would have a horizontal asymptote. So horizontal lines are y equals. I would have a horizontal asymptote at 3 over 1. Or we could say y equals 3. So if the degree on top is the same as the degree on bottom, I'm looking at a horizontal asymptote at the ratio of our leading coefficients. In this case, 3/1. And the last thing that can happen is, what if my degree on bottom is greater than my degree on top? So I carry a bigger degree on the bottom. If my bottom is greater, then I have a horizontal asymptote at 0. At automatic y = 0 is where I'll have a horizontal asymptote. So sometimes to remember the rules, you may hear top no, same co, bottom O. So that kind of reminds you of what's happening. So if my degree on top is bigger, there's no horizontal asymptote. If they're the same, then I'm at the ratio of the coefficients. If my degree on bottom is greater, I have an automatic horizontal asymptote at y = 0. So let's translate these rules to the example we have over here. How does my degree on top compare to my degree on bottom? Well, do I even have any x's on top? No, technically I have x to the 0, so it looks like my degree on bottom is greater. Well, if my degree on bottom is greater, I have an automatic horizontal asymptote at y = 0. So vertical asymptotes rely on our domain. Horizontal asymptotes rely on these rules over here. Then we have good old x and y intercepts. We've been talking about those with linear equations. We've talked about them with quadratic equations. Now we're going to talk about them with rational equations. Y-intercept, again, is that value of y when x is 0. So if I want a y-intercept, then I'm going to take my equation and put in 0 everywhere I see x. So we have a 2, we have a 0 minus 3. It looks like it's at -2/3. So my y-intercept, again, writing as an ordered pair, it'll be a specific location on the graph. My y-intercept is 0, -2/3. X-intercept then is the value of x when y is 0. This one's always a little bit harder because that means I have to set my entire equation equal to 0 and solve for x. But here's the thing about a fraction. We talked early on again in this course about when is a fraction equal to 0. We either had that it was okay to have a 0 on the top, or it was not okay to have a 0 on the bottom. So if I'm going to get this entire fraction to equal 0, I got to have a 0 in the numerator, in the top. So when I set this fraction equal to 0, I really only need to set the top equal to 0, the numerator equal to 0, because that's my only chance that that whole fraction will turn into a 0. Well, here I have 0 trying to equal 2. Am I ever going to get 2 to change and be 0? Not in this case. The top can never be 0 if I have a fixed number there. So it looks like in this case, I don't have any x-intercepts. And you know another reason why I have no x-intercepts? Because what's happening at y = 0? I got this horizontal asymptote there kind of blocking my graph where no points are going to end up on y = 0. No points are going to end up on x = 0. So it kind of makes sense that the algebra shows that way. So now that I've kind of listed the things from my chart, let's see how I can transfer them to the graph and how I can complete the graph as well. All right, domain is just a concept. I can't have any x's at 3. I have no hole to graph, but I do have a vertical asymptote at x = 3. So I'm going to dash that in at x = 1, 2, 3. I'm just going to kind of use the marker, so hopefully you can see on the graph. I'm going to have a vertical asymptote at x = 3, and I have a horizontal asymptote at y = 0. Again, might need to extend yours along outside the graph, just because it's sometimes hard to see that you've dotted in along that y = 0, the actual x-axis. And the only other point I get from my list here is 0, -2/3 for a y-intercept. So 0, -2/3. Well, not too much to actually know where I'm going to graph. But I do know a little bit about this parent function. This parent function mirrors that rational function, y = 1/x, and that was the one that had the 2 parts. the ones in each opposite quadrant. So I will expect that shape, and I will expect two parts of this graph in opposite corners. But if I'm honestly going to get the rest of this graph without the help of a calculator, I'm going to make a table. I'm going to want at least 2 points on either side of that graph, 2 points in one quadrant, 2 points in its opposite quadrant that I'm expecting, so that we can get a good shape of how to connect this. Looks like this quadrant already has the y-intercept, so we just need one other point on our graph. You can always make more, but I would expect at least one more. So what would be a good x to choose that would give me a point around here? Maybe 1, maybe 2, maybe I'll choose 2. So I'm choosing 2 for x, which means I'm going to plug in and see what I get for y. Well, if I put a 2 in here, I get 2 minus 3. So what's that? A 2 divided by 2 minus 3? A 2 over negative 1. So that's going to be a negative 2. Now I'm going to want some points over here because I'm expecting my graph to be in opposite quadrants, and I need something on the other side of that asymptote. So maybe I'll choose 3. Maybe I'll choose 5. Ooh, can't choose 3. Sorry, I didn't count correctly. 3 is where I'm blocked out. Maybe I'll choose 4, and maybe I'll choose 5. So here goes 4. We put in 2 on the top. Then we have 4 minus 3. So 2 over a positive 1 leaves me a positive 2. And if I put in a 5, we get 2 over 5 minus 3. That looks like 2 over 2. That looks like a positive 1. So let's see what these points do to our graph. I have positive 2, negative 2. I have positive 4, positive 2. I have positive 5, and a 1. So it looks like I'm going to stay within the boundaries of those asymptotes, and I'm going to get really, really close, but never touch or cross. Over here, those points did show from the opposite quadrant. I'm going to head towards that asymptote, again, getting very, very close, but not touching or crossing. And that's what I'm expecting most rational functions to look like. Does every single rational function have opposite quadrants? Not always. There are some special cases out there, but for the most part of what we're going to see, we're expecting opposite quadrants. All right, let's look at another one. Again, the more you do, the more these things flow a little easier. This one has an x plus 1 over x plus 4. X plus 1 over x plus 4. So if I'm going to do domain, I'm going to look at the denominator. Again, my eyes are focused on that denominator. Because it's a fraction, that denominator can't be 0. So what's my one value that will make the denominator 0? Negative 4. So x cannot be equal to negative 4. That domain's either going to be a whole or a vertical asymptote. I have a whole when I have a duplicate factor top and bottom. Do I have any matching factors? No. X plus 1 will not reduce with x plus 4. So I have no wholes, meaning that negative 4 must be a vertical asymptote. So I have a vertical asymptote. I'm doing x equals because it's a line at negative 4. Horizontal asymptotes has its own set of rules. So I'm going to go back over here where I compare the degree top and bottom. How does my degree on top compare to the degree on bottom? It looks like I have an x to the first and x to the first. They're a match. So since they are the same, my horizontal asymptote's coming from the ratio of my leading coefficient. Well, what's my leading coefficient here? 1. What's my leading coefficient here? 1. So 1 over 1 is 1, and that's where I have a horizontal asymptote. Again, I'm doing y equals 1 because it's a line. It's a horizontal line. Next we have y-intercepts, x-intercepts. Remember, y-intercepts that value of y when x is 0. So that means I put in 0 for x on the top, I put in 0 for x on the bottom, and it looks like we get 1/4. Again, our y-intercept will be in ordered pairs, so we'll turn it into 0, 1/4. X-intercept means I keep x and I make y 0. So I set the entire equation equal to 0. But if I want that fraction to be 0, I really just need the top to be 0. Doesn't matter what I have on the bottom, on the denominator, if my numerator, if my top is 0, that whole thing, 0 divided by whatever we got on the bottom, is going to be 0. So what will make x plus 1 equal to 0? Negative 1. So I have an x-intercept at negative 1, 0. So let's plot what we have, and then we'll make that table and complete the graph. All right, I got a domain at negative 4, no holes, and that domain is blocked by a vertical asymptote at negative 4. So there's my vertical asymptote. I have a horizontal asymptote at y equals 1. Kind of making that grid, making those 4 corners. I got 2 points this time. Y-intercept at 0, 1, 4. So just barely above that x-axis, and an x-intercept at negative 1, 0. So I actually got 2 good points in that quadrant. Might even could go ahead and connect and say, I know this is going to head down towards the vertical asymptote and get closer and closer to the horizontal asymptote. But is my graph complete? Not if I know what a rational function looks like. I'm expecting graph in opposite quadrants. So I should have some graph over here that I need to find out about. So how am I going to find out what's happening over there? I'm going to make a table. And I need to see what's happening over here. So I need to go along the x-axis and choose some points over here that will give me the points I'm expecting. So anything basically beyond negative 4. Negative 5, negative 6, negative 7. Maybe I'll do negative 5, maybe I'll do negative 7 to kind of see what's happening out towards the left of that graph. Then I plug in. So I'm doing negative 5 plus 1 over negative 5 plus 4. So what does that give me? A negative 4 on top and a negative 1 on bottom for a positive 4. If I put in a negative 7, we get negative 7 plus 1 and negative 7 plus 4. So what is that? A negative 6 on top and a negative 3, positive 2. I just happen to choose those values. But again, let's see where they graph. So here we are at negative 5, up 1, 2, 3, 4. And I have negative 7 and positive 2. Again, expecting graph in that upper quadrant. So I'm making sure that these points are probably right. I should probably feel pretty confident that the graph is shaping up like I expect. And so there's that completed graph. So what we don't get from the list, we're going to get from a table. All right, very last one. X squared minus 2x minus 3 and x squared plus 3x plus 2. A lot of what we're looking for is based upon factors. And so it's probably going to be a whole lot easier if we look at this in factored form to get our attributes of the graph rather than in the standard quadratics we're looking at top and bottom. So let's see if we can factor. Is there anything that will multiply to be negative 3, add to be negative 2? Looks like x minus 3 and x plus 1. On bottom, same thing. I have what multiplies to be positive 2, adds to be plus 3. What's that? Plus 2 and plus 1. Might be a little easier now to analyze. Let's do domain. Where do our eyes go for domain? If I'm dealing with domain, because it's a fraction, I'm focused on that denominator. And that denominator is, or I need my denominator to not be 0. So what will make my denominator 0? Well, I can't have a negative 2, and I also can't have a negative 1. So I have 2 spots that are bad for the domain. X can't be negative 2, nor can it be negative 1. Holes. Here we have a situation with a hole, because we talked about when does a hole occur. A hole occurs if I have a duplicating factor top and bottom that divides out. So because my x plus 1 is a match, that means that this negative 1 problem in our domain is going to be a hole. So I'm going to have a hole at negative 1. But a hole is just a tiny little point, a tiny little gap that my graph didn't have an output for. So kind of like that vertex, I need to be able to complete it. I have the x, but I need the y that goes with it. So if I'm given any x, how do I find the y that matches? I plug it in. So I'm going to take this x and plug it in, and I'm going to plug it into just what's left over. Because if I plug it into the original, I'm going to get that 0 in the denominator. So here we go with -1. I would have -1 minus 3 over -1 plus 2, -4 over 1. So it looks like my whole is completed at y equals -4. So -1, -4 will be where my whole is. Well, I still have something to account for in my domain. -2 would also create a 0 in the denominator. So because nothing canceled with x plus 2, that means this -2 that was in my domain, it must be the vertical asymptote. So a hole occurs when I have a duplicating factor. Whatever's left over as a single must be a vertical asymptote like before. So I'm going to have a vertical asymptote at x equals -2. Everything in this list has to be accounted for as either a hole or a vertical asymptote. Horizontal asymptote plays by its own rules. Again, that's where I compare the degree on top to the degree on bottom. In this case, we're looking at the same again. I have x squared, x squared. If my degree is the same, then my horizontal asymptote comes from the ratio of my leading coefficients, which in this case is 1 over 1 again. So we're looking at y equals 1. Y-intercepts is where x is equal to 0. I can go back and do just what's left over here. I can plug into the original, whatever works. So I think I'm going to go to this what's left over, 0 minus 3 over 0 plus 2. Looks like -3 halves. X-intercepts where I make y equal to 0. So I'm going to set the entire equation equal to 0. Again, using that factored form because it's a whole lot easier to analyze with the factors. If I want my fraction to be 0, that means I want my top to be 0. So what will make x minus 3 a 0 in the numerator? Positive 3. So I'm going to have an x-intercept at 3, 0. So let's see what we got. This time I have a hole at -1, -4. So a hole is just a tiny little open circle that says, you know what? I can't fill in that point because when x is -1, I get a 0 in the denominator. So it's just a tiny little gap in my graph. I also have a vertical asymptote at x equals -2. So at -2, I'm going to build that block to the graph. Also have a horizontal asymptote at y equals 1. Again, setting up those 4 corners. I have a y-intercept at 0, -3 halves. What's that, about 1.5? And I have an x-intercept at 1, 2, 3, 0. So I have a pretty good idea about this bottom right quadrant here. I'm expecting it to head towards that asymptote. I get close to that hole and I just skip over it and keep going. It's literally a hole, a little splotch in the graph that my graph won't go through. My graph complete? No, because I know enough about rational functions and I'm expecting graph in opposite quadrants. So how do I complete the rest? I'm going to make a table. I just want to see what's happening over here so I can accurately give part of that graph. So I need to get beyond x equals -2. So maybe x equals -3, maybe -4, maybe -5, something like that. So if I put in -3, again, I'm just going to go back to that easy what's left after I canceled out those x plus 1s. So I have -3 minus 3 over -3 plus 2. So what's that, a -6 over -1? So we actually get a positive 6. Makes sense. I'm expecting it to be pushed up into that top left. -4 says -4 minus 3 over -4 plus 2. So what's that, a -7 over -2, so a positive 7 halves, 3.5. So here we are at -1, 2, 3, up 1, 2, 3, 4, 5, 6. And here we are at -4, and what's that, 3.5, 1, 2, 3, 0.5. Again, making sense for what I'm expecting this graph to look like. So more than likely, I'm left with just virtual students writing or watching this video at the moment if you are in the fall of the 2020 school year. So let's do a giveaway. Virtual kids, if you've made it this far on my video, send me an email that says, hey, Miss Tip, I saw your entire video and know about the giveaway. So just say, send me an email with, I watched the video, and I'll see what I can do for some little fun contest for my virtual kids. So again, we'll spend today in graphing. We'll spend tomorrow as well practicing. So hopefully by exam 3, graphing will be smooth.